Hola, hola, hola. ¿Ganancia? Ah, listo, igual, están igual.
avisas, ¿no? Me avisas. Bueno, buenos días para todos. Es un honor para mí presentar nuevamente al profesor Carl Henrik Eck, una destacada figura en el campo de aprendizaje automático y el modelado estadístico. El profesor Eck es catedrático de Statistical Learning en el Computer Laboratory de la Universidad de Cambridge y también ejerce como profesor visitante en Machine Learning en el Instituto Karolinska de Estocolmo, donde colabora en proyectos interdisciplinarios que integran inteligencia artificial y medicina. Su investigación se centra en el desarrollo de modelos probabilísticos que manejan de forma rigurosa la incertidumbre, permitiendo el aprendizaje eficiente a partir de pocos datos. Su trabajo combina enfoques bayesianos, procesos gaussianos y técnicas no paramétricas con un fuerte énfasis en la interpretabilidad y la utilidad práctica. Con una trayectoria internacional que incluye instituciones como UC Berkeley, el KTH Royal Institute of Technology y la Universidad de Bristol, el profesor Eck ha publicado más de 90 artículos científicos y ha contribuido a aplicaciones en áreas tan diversas como la percepción robótica, el diagnóstico médico y la predicción climática. Nuevamente, por favor, demos una cálida bienvenida al profesor Carl.
Thank you very much. Great. It's good to see roughly about the same number as yesterday, so we didn't scare too many people off. So I'm happy about that. So today, yesterday was a lot of setting the scene, trying to give you a bit of perspective where I come from. Maybe you agreed, maybe you disagreed. Fantastic. If you disagree, I'm much more interested in that. Then we can have a long chat about this afterwards. So today, we're now going to try and ramp this up, and we're going to talk about some interesting models that allows us to do interesting things. And then tomorrow, I thought it was this afternoon, but it's tomorrow, we're going to do a talk of showing how we can use these in a scientific setting. So basically today, we're going to talk about Bayesian non-parametrics. So just a super brief recap of the two things that I really wanted us to get across from yesterday, right? Super simple learning theory. The thing you can think about any learning algorithm, we have some space of hypothesis, we have some form of learning algorithm, the thing that effectively allows us to navigate the space of hypothesis. We've got some finite data set which follows some data distribution. We have this data distribution, we're all fine, right? There's no learning to do. The only thing we know is that we hope that these are somehow good samples from that distribution. And then we have some form of measure of quality. We can call it loss function, which effectively says if I apply my algorithm A to the hypothesis space H on this finite data set, this will return me some form of predictor, regressor, something what it is, that can then be evaluated on this data, which allow me to somehow compute how well I'm doing on a specific data point, right? We said, great, so what would learning actually be? Well, the sensible way to learn would be to somehow compute what's called the true risk, or the expected error, where I would just take the expectation over this loss over the data. This is completely impractical, infeasible, right? Because this integral would require me to have the density of the data. If I have the density of the data, I'm already done, right? So what we do is that we approximate this with the empirical risk, where the empirical risk is effectively saying, I trust the data that I have, and I'm just going to average that, right? Okay? Now, the tricky thing then, the thing that we always thought, I said it twice yesterday, is the no free lunch, right? Thing is, I can come up with a combination of training data, an algorithm, and a hypothesis space that are equivalent on the empirical risk, but makes the true risk take a completely arbitrary value. If you want to think about it, is this. the empirical risk of each of these functions are the same. The true risk is fundamentally different, right? It has to be, right? And actually what it means is that if I look at this line, the set of functions, so say if I take the hypothesis space is every function that exists, right? I can take a function, there exists function that passes exactly through these red dots, so empirical risk 0, that gives me any value between plus and minus infinity on this point, right? Okay, that's the no free lunch. So we then talked about, of these three elements that I got to deal with, how can I input constraints, right? How can I input priors, beliefs, whatever I need to know. I got a super badly posed problem, and I need to constrain it somehow. So I said first, you can think about A. This means in some way I control the search algorithm. I say over there is the, say, the problem I had before, and I want a smooth solution. I say all the high-frequency solutions are there, so I'll put an eye patch on my algorithm, it doesn't see it. I say all these very narrow solutions that are very good, but very close to them, they're really bad. So I put clown shoes on so I don't fall into them, and so forth, right? The other thing would be to do some form of data augmentation, where I know I want the solution to behave like this. For example, I might know that the solution should be rotationally invariant. So I take all my data and I rotate it. Now, the empirical risk will somehow constrain that. Or the final thing is then looking at how we can constrain our hypothesis space. This is what we did yesterday, where we did something as silly as doing linear regression with 1 and 2 parameters. Now we're going to think about doing this in a much more clever way. So the way we're going to do this, the way we're going to put these constraints in, rather than putting hard constraints, because I don't trust myself enough to put hard constraints in, I'm going to put probabilities to constrain things. I'm going to say something that if this is some form of parameterization, I would say, I like these parameters. They're more believable than these ones, and these are also more believable. So we said, great, if I can do this, then I can implement all the constraints effectively using Bayes' rule. So I talked a little bit about the interesting thing just to my view of thinking about being a Bayesian, or how a Bayesian would think. The object that's really interesting is the denominator in this case, where I integrate out all the possible beliefs I have, and I average them over the data, right? So this gives me a measure of how good my beliefs with my hypothesis work on this data. The way I like to think about this is to give a more, I think, intuitive explanation of this, is to think about this object here. This is a measure. It's the canonical measure of a space. It's chopping up a space in equal points, right? When we learned Riemannian sums, right? When we learned how to do integrals in our first calculus course. This is also a measure. It's a probability measure on this space. When I combine these two, I'm effectively creating a new measure over theta that reflects my beliefs. That's the easiest way to think, I think, about what it means to marginalize. So in some sense, I have theta. I like these things. I don't like these things. Now I'm going to stretch that part of the space, and I'm going to make that part of the space tiny, and now if I throw a rock in there, well, it's much more likely to land where I want it to be, right? That's effectively what marginalization does, right? There's probably some much more nicer explanation of this, but I get the intuition from that. Cool? So, great. So then we talked roughly about how these combines a little bit more visually. So we said, if I got my likelihood function, the thing that says, if I know the slope of a function, what do I think probable data is? Here I got two functions. This one thinks data lies here. This one thinks data lies here. I say three different priors on this. One that likes negative functions. Oh, is it this one? Oh, I'll have to stand like this. Let's see. Maybe it's, what have I done? Okay. I'll put that. Is it me? Okay, we'll see. I'm quite loud, so I can shout, no problem. Here, I got something that likes negative lines, positive lines, and this one is very vague. This here is the evidence, right? This is the integral of this. So now what you effectively do with this measure, the way of thinking about it, the way I said about stretching, is that this thing is green actually everywhere. There's just a tiny shade of green here, and then it gets stronger and stronger and, tiny. The evidence, the stretching that we do, is effectively taking this set of lines and making this space equally green, right? The transformation that will make that equally green. That's what the green model represents. The blue one, same thing. So it's going to make that space of line much, much bigger, that space of line much, much bigger, okay? That's effectively how you can think about that. Right. So then what you can do with this evidence term, this we didn't talk about last time, is to say, cool, I take these linear functions, I compute some evidence, it looks like this. I can also take, we said I take these non-linear basis functions, I evaluate something like this, right? The evidence is going to look like this. Now it ends up with two different plots, right? So it basically says that the line thing, it likes things that looks like this. So I evaluate the evidence under some data that looks like this. It's going to have a decently high measure. If I have something that looks like this, it's going to have a very small measure, right? So now what that means, I can do model selection, right? So if I have some data, then I can evaluate which one has the highest evidence under these two, right? And then I can do model selection using this. And another plot, and this was made famous by David Mackay in his PhD thesis in 1991, and this is usually the argument for why people say that Bayesian models does automatic model selection, is that if I would be able to, this is a leap of faith, if I would be able to order all data sets from very simple to very complicated, right? If I have a model that places probability mass in this region, so it's capable of modeling, it's happy to say I can model these, because the density has to sum to 1, it naturally needs to put less probability mass everywhere, right? Something that can explain a lot of things has to also put less mass at each point, right? And then you've got something very simple, it's therefore going to be high where it is high, right? So now, if this is actually the data I have, I can evaluate the evidence under these. The model that I should pick is the model that is, it explains the data, but it's as least complicated as possible, right? This is effectively the notion of Occam's razor. I like this plot because it explains a lot of things, but it fools you a lot, and we're going to get to that now. So, you'll often hear this notion, Bayesian inference will automatically perform model selection and choose the simplest possible explanation that's consistent with the data. That's what my plot told you. The notion of simple is relative. To begin with, how the hell do you sort the x-axis on this? Give me a way to sort from simple to complicated data set. The notion of simple is relative, right? It's very relative. For someone who's a marathon runner, running a marathon is simple. For a lot of people, well, for me in this room, running a marathon is damn hard. But I bet you, for that marathon runner giving this lecture is really, really hard, right? So, the notion of complexity is relative, and this plot doesn't show that. It fools you out of this. So where does then, so the key thing is, any machine learning algorithm, we talked about this, can only be interpreted relative to the knowledge that it puts into it, that it refers to. So what that means is the posterior can only be interpreted in light of the prior. And in some ways, I think one way of thinking about prior distributions is that they define the notion of simplicity, right? When you say, I have a model that can do linear things and I like slopes that are negative, you define what simplicity means. Negative slopes are what you've said simple is. So, even though this framework allows you to do model selection, you define simplicity, right? So if you've defined that, you can do it. And that's often not brought up. It's brought up as a notion, this will just automatically work. It won't. So, the most important plot that we therefore showed yesterday, these are all the simplest explanations, but they're fundamentally different, right? Remember, we had one, where we had a prior prior that was really strong, very far away from the true solution. We saw 2 data points. Now, these are the simplest possible explanation of that data under the prior. Then we changed the prior, or we had another prior that was like really fat. We see the same thing, now this is the simplest thing, right? The change is the prior that we put into it. So that's why priors are super, super important, right? And for those of you who saw my talk yesterday, that was the whole thing I brushed over, right? The prior that I used, I told you on the last slide, it makes no sense. So basically you can ignore everything I said yesterday. Cool. So, to then go on to what we're going to talk about today. The Bayesian argument implies that you try to reparameterize a hypothesis space to reflect your beliefs. A good analogy, as I tried to do, is to think about space of believable parameters. And now, you can think about the stuff I talked about yesterday in composite models. You can think about this as directly altering the parameter space for an optimizer. So, what is then a good parameterization of the things that we want to learn? So, I want things that are flexible. So what I mean by flexible is that I want to have a class of models that can describe a whole load of things, right? So I want a parameterization of an object that contains loads of stuff, right? But I want to be able to control this flexibility so that I don't need an enormous amount of data, right? If I say I want to model with the whole space of functions, right? That's great, but you're going to need an enormous amount of data to tie this down. So what I want is that I want to be able to specify a probability distribution on this enormous space that can be super, super narrow, right? So that I can have a very strong belief, right? And I want the parameterization to somehow be interpretable. So when I get my posterior distribution, I can interpret it based on what I put in. I said, I'm looking for smooth functions of this degree. My result comes out. Now I can interpret that result in, if I said I wanted these functions, this is what it gives me. If I can't do that, nothing matters, right? If you can't specify your hypothesis, you can't do experimental testing. So today we're going to try and define a very, very useful prior distribution that has exactly these characteristics. So to do that, we're going to talk about non-parametrics. So what we're looking for, we're going to do regression the whole day. So in some sense, we can go back to the problem that we had initially. I have these things, and what I want now is that I want to be able to have a measure that I can control. So for example, if I really like these kind of functions, I want to have a higher posterior distribution over those and those, right? Or vice versa. That's how I want to control things. So we are going to think about this non-parametrically, because parametrically this is really weird, right? How do you even specify the parameter space that contains these three functions? It's kind of tricky, right? So when things are tricky and we don't understand things, at least I go to beer, right? That's the solution to most things. So I'm going to try and explain non-parametrics through beer. So I like beer a lot. There's some really nice Colombian beer. I still haven't tried the Club Colombian Red. So I still haven't found it. So that's my aim. I got 2 days more. Cool. So now, if I had a beer yesterday, and I'm going to explain it to you, right? I want to say, you know, you should really try this one. It tasted like this. And now I'm going to try and explain this. The obvious thing to do, right, is I'll go and ask the brewer for the recipe. The recipe is a parametric model. It says this much hops, and then you do this, and then this much barley, and you do this. There might be some brewer in this room, but I guess for most of us, it means nothing, right? Right? It would mean absolutely nothing. It's completely useless parameterization. So what do we do as humans? Well, we said this thing, right? You know, yesterday I went to the Bogota Brewing Company, which is close to my hotel, and I had this porter, and you know what? It tasted a little bit like that beer we had in Bogota a few weeks ago, but the head changed a little bit, so it was more like that other thing we had on Tuesday, right? I gave an explanation that now relates the new thing to previous knowledge, right? Not going through parameters, but going through the object itself, right? This is what we refer to as non-parametrics. So then, let's stop doing beer, and let's talk about this in a bit more boring terms. So I have a space, and I have a point in that space. And I now want to describe this point, right? Well, there's nothing I can do, right? I can explain its coordinates, but I have nothing to relate it to. This is like your first beer, right? You have nothing to relate it to. But as soon as you've seen something else, now you can say, oh, these two somehow relate, right? You can do the simplest thing, a nearest neighbor, right? That's the simplest non-parametric model that exists. You say, well, what's closest to this? Now, as soon as you see more and more things, it increases your representational capacity, right? Because you have more things to relate to. So now, what you can do, you can either do the very silly thing, right, and still do a nearest neighbor, or you can come up with some form of distance measure or something else that relates these, right? So now we've transferred the problem to representing the coordinate of this thing to coming up with a way of thinking how do things relate so that I can represent this thing, right? Here I've just done Euclidean distances. You can do something like this, like a shortest path between these points. You come up with loads of things, right? Now, very often when I work, especially clinically with medicine, people there, this is a supernatural explanation, right? Because that's exactly how we think all the time, right? We relate things to previous experiences, right? When they see a patient, they think, oh, you know what? Last year I had a patient yes, exactly, great. That's information I can work with, right? Relative information. So, that's basically the basics of non-parametrics. So now let's try and do math of this, right? We want to deal with functions, right? We want to build non-parametric representations of functions. Whew. That's a bit tricky, right? So let's think about what we know about functions, right? So if I draw a line here, functions behave in very peculiar ways. Of any function that's defined over the real line in this case will cut this line once and only once, right? If it cuts it twice, it's not a function, right? So that's something I know is true for every function. So now, I want to be a bit probabilistic about this. So I'm going to quantify where the function cuts this line using a distribution. And I'm going to call that, I'm going to use a Gaussian distribution in this case, yeah? So now, I can do that. Well, there's nothing special about +3, so if you agree with my argument here, you would agree with my argument here. It's the same thing, right? Any function will have to cut that and have to cut that. Cool? So what I now have is that I've parameterized a function through its value at a specific location. So I got f1, the red one, parameterized as the Gaussian, and f2, I've parameterized that as a Gaussian, okay? Not super interesting just yet. So what is the other thing we know about interesting functions? Well, interesting functions means that if I would know the value here, that would somehow constrain the value here, right? There will be information flowing from this to this point and this to this point, right? So let's say I've observed that the actual function I'm looking at cuts -2 at 2. Now, let's say I have a little bit of noise. I don't trust myself completely, right? So I think it cuts there, but so I have a very small variance Gaussian. Now, I could either say, knowing this value constrains this value nothing, right? So now nothing happens, right? It's the same Gaussian as I had before. Or I can say, knowing this point tells me everything about this point, and it's exactly the same. Or maybe it's somewhere in between, right? So now we're starting to get somewhere, right? So effectively what I've done now is that I've said these two values, function values, f1 and f2, are jointly Gaussian, and they had variance, which was our prior variance, K11 and K22. Now, the interesting thing, the thing we showed about how the variance changed knowing one of them, that's the covariance element, right? So these two. So let's just do a brief thing on two-dimensional Gaussians, right? Just to get our lingo correct. So I got a joint distribution. So in this case, I got F1 here and F2 here. Now, it's a slightly tilted Gaussian, so there's a covariance object that's non-zero. Now, if I see F1 being this value, it induces a distribution. This has 0 mean. It induces a distribution that has a slightly higher mean than 0, right? So these are the slices that I've drawn. So I have a two-dimensional Gaussian, but you have to think about the plot I had in the previous case. I can make the covariance really, really high, right? Now you'll get something like this, right? If I know x1 to be 1, well, this distribution is nearly peaked around 1, right? And if I make them completely independent, they're all the same, right? Cool. So what we can then do is that we can parameterize this covariance object, which is exactly the same thing the CES tells us. How do these two things connect? How did the two bears that we had connect, right? So let's do that. Let's specify a super, super simple Gaussian. This one here. I don't know what the covariance is, but it's slightly bigger than 0. And then I have my two slices at -2 and 3. And what I'm going to do now is that I'm going to draw a sample, and I'm going to draw a line between the two. Oops. You can see the characteristics of these samples, right? So they will be dependent, but they would vary, right? Right? We don't see lines going like this, and we don't see super flat lines. If I now change the covariance and make them super, super covariant, right? Now every line is basically flat, right? If I know this one, it basically tells me everything about the other side, and vice versa. And if I take the independent one, we've got lines going all over the place. Cool. So we've drawn lines. Not super exciting. Well, the thing is, there's nothing special about this one. There's nothing special about this one. So I can add a third. I mean, they're three-dimensional Gaussian. I can add a fourth. I can add as many as I want, right? How many indices can I find on the real line? Well, it's uncountable infinity. So I can draw as many lines as I want. So that means I can write up a multivariate Gaussian, which is as big as I want, right? So now, there's a very cool thing about the Gaussian, which makes it very, very special. There's two cool things with it. The first thing is the marginal property of a Gaussian. And what that means, it's just so natural, so we don't even refer to it as a property. If I would have this two-dimensional Gaussian, defined exactly like this, and now I would integrate out x2, so I would look at the marginal distribution. We know how to do this, right? You just pick out the mean and the variance. It looks like this. If I instead define an n-dimensional Gaussian, where these two are the same, and if I integrate out everything else than x1, I get exactly the same value, right? This is called the marginal property of the Gaussian distribution. So what that means is that if I have, say, 100,000-dimensional Gaussian, and I look at the marginals, x1 and x2, right? Looks like this. And then I look at x1 and x42. Oh, I've swapped the indices. x0 and x42. Sorry, my bad. This thing is the same as this. Nothing's changed. So, this is one part of a property of a theorem called Kolmogorov's extension theorem. And what it says is basically this. If you have, for all permutations pi, measurable sets fi, which is a subset of Rn, and probability measure v. The marginal property was the one that we stated. If I take the measure evaluated at the subset, that's the same thing as taking the measure evaluated on that and you extend it, right? And then it has an exchangeable property, which is absolutely trivial for a Gaussian. If I take a permutation and I exchange the measure, and I also exchange the things I'm measuring over, that's the same thing. What this theorem tells us is that if these two things hold for a finite distribution, this finite distribution can be thought of as an object that's infinitely big. It's a projection of an infinite object down to finite things. So what that means for us, and importantly, the finite object is consistent with the infinite. So what that means is that we do something as cool as this. So let's take our Gaussian, our two-dimensional Gaussian. Let's draw a sample, right? We saw how we do this. But this two-dimensional Gaussian is consistent with a three-dimensional. So I'm going to draw a sample from that. Well, this three-dimensional is consistent with the five-dimensional. Oops. So we can draw that. That 5 is consistent with the 9, with the 17. I can keep going. What does that look like? A function, right? I can effectively do this if you think about a function as just an infinitely long vector of values. That's how I parameterized it. So I can draw multiple samples. Dunk, 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 dunk. Oops. And I get something like this, right? Super cool. So this has only been the finite case. I can do so in the infinite case as well. And that means I can just extend this Gaussian and think whatever size Gaussian I'm working with, I can think about this as a set of marginals from an infinite dimensional process. And that's called a Gaussian process. So another way I like to think about it is you've got this object that you can never ever write down. No, it's impossible to write down. It's infinitely big. But I can take any projection of this. I get just a normal multivariate Gaussian, and I can work with that. But I know that this object is consistent with this. And this is a measure over the space of functions. Cool. So another way, the definition, a Gaussian process is a collection of random variables, the output of the function at a specific slice, who are jointly Gaussian distributed, indexed by an infinite index set. So now, the slightly annoying thing that we had before was that, yeah, this is great, right? But how do you specify these matrices? Right? These matrices are gigantic, right? Well, we can specify the mean and the covariance as a function, right? So the way I can do this is that this here, remember the plot where I had a black dot and I drew things? The thing I want to parameterize is how one thing correlates with another thing, how two things relate. This is exactly what the covariance object does. So I'm going to specify a function, in this case I'm going to call it k, which takes x1 and x1 in this case, and this gives me the variance of that slice. And here I parameterize with x1 and x2, and it computes, dependent on the input location of these slices, how much I think they covary. If I can write that up, I can write as big of a matrix as I want. So we parameterize the covariance as a function of its input. The index set to this is the uncountable infinity, because it's just a real line. And this is your handle to input knowledge into a Gaussian process. This is the covariance. And the covariance function is the thing that's going to characterize how the distribution places probability mass. So you specify the degree of covariance between data points. If this parameterization makes sense, this is a really good object, right? It's a really good way to work with things. So what can we do? Simplest thing that I can think of, smooth functions. So it basically says the closer two things are in X, the more they covary. The further away they are, the less they covary. So I can do something like this. I can say a covariance function that has an exponential fall off in distance, right? The closer they are, they covary. The further they fall apart. If I draw samples from that, I'm get something like this. I can, in this case, I divide it by 15 there. I can divide by 1, I get wigglier functions. I can divide by 150, I get not so wiggly functions. The cool thing, though, remember what I said, I want things that are narrow, but I want them to be flexible. Is there any function that doesn't exist? Is there a function that has non-zero probability? Can you give me a set of points where my distribution would say 0? No, because a Gaussian has infinite support, right? Plus infinity to minus infinity on every slice. So everything exists. It's just that by writing this covariance, I put this like super narrow probability distribution on a specific object. Because if you look at these, they all look exactly the same, right? This is not diverse samples. They just look diverse because if we think in our parametric heads, if I had to write that down in parametric form, you know, that would be really hard, right? But now it's actually very simple, okay? So just one of the things with Gaussian processes is hopefully you think this is kind of cool if you haven't seen this before, and people think, wow, that must be tricky. The plots I have, this is the Python code for generating these plots. So it's effectively, I do a linspace, I compute a covariance matrix, I have 0 mean, and I sample from a multivariate Gaussian. That's it, right? It's as simple as this, right? It's absolutely trivial to generate these plots. Cool. Other things you can do super easily, right, is to write periodic signals, right? It's just having a covariance that's periodic. You're going to be able to draw periodic functions. There's loads of things you can do with covariance functions. There's a whole set of things. So for example, you can add covariance functions together. You can multiply them. You can do linear transformations of them. This one is really cool. If you have an input space X, and you write one covariance over a subset of it, so you take like the first 10 dimensions, plus the second 10 dimensions, it's a covariance over the whole space, right? You can do lots and lots of different things that allows you to design very specific covariance functions. So with that, I would be able to have a measure so that I can evaluate which one of this is consistent with my prior assumptions. So, cool. Do we have any questions now? This is a good point to take questions because we're going to go to inference now. Oh.
¿Alguien tiene preguntas?
No? We're all happy. Wow, good. Or we're all frustrated. We don't know. Okay, please stop with questions, right? So, what we've done so far is that we've defined a prior measure. So we have something that can quantify, specify a density over the space of functions. Very cool, right? But it's only cool if we can use it, right? So what we want to do now is do inference, right? Specifically, what I want to do is that I want to say, I've seen the function at a specific set of locations. Now I want to say what the function is at another set of locations, right? Cool. So that implies doing base rule. Now, this looks a little bit insane here. I now want to integrate over the space of all possible functions. Good luck, right? You're not going to do that. So let's think what it is that we actually want to do. So this integral effectively enumerates every possible function and it pushes them through here. Yeah, not going to happen, right? So let's think visually what we want to do. So here's my prior. I've sampled everything, well, a lot of A from this prior. Now I see a data point, and I basically want to write an if statement, a for loop, for each of these. If going through that point, keep. If not, drop. Exactly. Yeah, you're not going to do that either, right? I can draw infinitely many samples here, so it's not going to happen. Turns out that this is absolutely trivial to do. So let's think about this again. So I have my joint distribution of my data that I've seen with the data that I want to see, the function values that I want to see. That is the posterior distribution here, right? So the posterior distribution of the things I want to see, given the things I've seen, times the prior. Now, this thing here we've defined, right? I said any marginal is consistent with a bigger object, right? So this is just taking what we've defined and you're saying, I'm just going to add a few locations to it. So we know what that one is. We know through the marginal property that this thing here needs to be consistent with that. That's just dropping those values and I got this. And then finally, we know by Gaussians being closed, we know that this thing here has to be a Gaussian, right? So now I know this object and I know this object and I don't know this object, but I know it's Gaussian. Now you can just solve this by identifications, right? So you solve for the posterior distribution in that equation. Super, super simple. So what I do, I say, this would be a matrix now, right? So I've concatenated loads of points here. Here is the covariance, there's the cross covariance. These are the points that I want to see. Now, it's just a simple conditional Gaussian, so this object just becomes this, right? And you can actually see this has quite a nice formulation of it. You can see that the mean is just a linear predictor, right? It's just a linear scaling of the points that I've previously seen. And the covariance is the prior covariance corrected by how much information X tells you about X star, right? So very, very simple. So I see some data points. If we look at these data points, now I'm going to show you a matrix which has been computed. I do X star, so the values that I'm going to look at the function, I do loads of them here. Can't remember how many. Not too many. Okay, this here is the values that I've seen, or the X locations that I've seen, and this here is the values where I'm going to calculate this from. So if I multiply these two matrices, this is the thing I get. Blue is roughly 0. Now what you can see, what's happening, is that I multiply this by f, which is the functions that I've seen. I basically got zeros times f. That means all the way out here, I'm saying I can't use any of this data, right? Okay? Then you get into some middle of the data. Some part of the middle of the data where you're closer to this. It starts saying, oh, now I can start using these data points. So it's just a linear predictor. Super, super easy. That's the mean. The covariance looks like this. I have my prior covariance on smooth functions. So it says that points that are close to each other covary this object. And then I have this object, which is effectively how much information does these tell me about these. It's this whole thing. That is this. And then I subtract this from this. And I end up with an object that has variance away from the data and no variance in the middle. Right? So if I draw samples from that, I'm going to get something like this. Right? So I just now took, say that in this case I had 4 data points. I just generated a 204-dimensional Gaussian where I just Lin spaced this. Cool? You can look at the posterior process instead, so I can plot standard deviations, look something like this. And just to show you an iterative process, just to get visually what this means, I got this function. This is my prior. Now I'm going to give you one point after another point, and we're going to show how this uncertainty changes. So I see 1 point, boom, snaps in there. 2 points, dunk, dunk, dunk. Something like this, right? So uncertainty gets reduced because I had, in this case, a prior on a very smooth function, and data points this close, it can't really move anywhere, right? So it's a very, very constrained model. Great. So let's look what we now have. We have defined a measure over the space of functions. We've shown how we can do Bayesian inference really trivially with that. And now the nice thing, by having this K object, we can really think about how, in a very useful and domain-driven way, we define this, right? It's exactly that thing of, you know, a doctor, which patients are similar to other things. Like, you know, it's a very, very simple way of elucidating priors. And from this, we then got this updated measure that combines knowledge with data. So let's then take this a step further. So what we've done, if you're familiar with graphical models, we've effectively worked with this model. I have some input, and then I have a function, I have some output, I have some parameters, which are usually then the parameters of the covariance function. So we sort this object here. Now, we can also do unsupervised learning, right? So let's say I only have y, but I don't have any x's, right? So let's think about what that problem is. I always think about unsupervised learning in this way. Remember when we had abacuses to learn how to do math, right? And we move these balls around, right? That's how I think about unsupervised learning. I've been given y, but I have not been given x. And my task is to give each of these an x position and combine them with a function, right? That's a solution. That's another solution. Let's see, that's another solution, right? But this is an even more ill-posed problem than the one we had before, right? But let's say that if I had a prior on the functions, you know, that would be a great thing to have. I could say that I like functions of a specific kind, and I can just rank these solutions, right? Then I would do unsupervised learning, right? That's it. So let's take a GP prior, and let's put the x location in this place, right? I can evaluate it. I can put them in this place. I can evaluate it, put them in this place, and so forth, right? Now I can do unsupervised learning, right? With exactly the same framework. There's no difference. It's just now your input is also random. Okay? Was that reasonably clear? I just don't like when people make this big thing about supervised and unsupervised learning. To me, they're just the same. There's no difference between the two. If anything, unsupervised learning should be called more supervised learning, because clearly it's a worse constrained problem, so it needs more supervision, right? Okay? I don't like this dichotomy at all. It's just regression. The end, it's just that you don't know your inputs, they're random. Ugh, how different is that? That's not particularly strange, right? Cool. You can also do what I talked about yesterday. Well, if I want to build a composite model, why not just build them as compositions of Gaussian processes? Now I'll just push one Gaussian through another Gaussian process and so forth, right? And that should solve everything. It doesn't, by the way. So let's then take stock before we go to the last thing. I need to keep track of time. So regression is ill-defined. It's an ill-posed problem due to the no free lunch because we don't have any constraints on the functions, right? A Gaussian process prior provides us with a measure that we can encode our beliefs in so that this big problem becomes well-posed. And we can do inference in closed form. Unsupervised learning is just an infinite number of possible combination of input locations and functions, but clearly input locations and functions are very tied to each other, right? So by just placing a prior over how I want the function to combine, I'm effectively inferring both x and f, right? So, do we have any questions on this? Yes, shoot, thank you. Oh, you can do this.
Thank you. Get the microphone.
Thank you. Oh, perfect.
If the prior is so flexible, why is it possible that the result isn't always a function? Is always a function.
Yeah,
It's very strange.
yes, it is very strange, and this is one of the things that baffles us. Oh, sorry. It is very strange, and it's a really astute insight that you got. So it is very odd, and this is the odd thing about high-dimensional statistics, right? If you take a Gaussian and make it, you know, we see these nice, beautiful Gaussians in 1D and 2D, and they look like they're big blobs. In very high-dimensional spaces, they are basically delta, oh, they're not delta functions, but they're absolutely tiny, right? They're super, super, super small, right? And I can control the width of them, I can, but then it becomes very, very bland. So the covariance that I've written, in this case, are very, very narrow that sits at a specific point, right? So even though it puts non-zero mass everywhere, so your question yesterday, if I would have data that really wants me to get there, eventually will get there. It will take a long time. But if it fits with my beliefs, actually, I'm going to have a very small amount of data and I can do inference, right? So that's the trade-off one will have. So that's what I meant, that these are flexible, yes, represent everything, but they're super narrow, really, really narrow. There's another question on that, which I haven't poked at yet. Let's just get, which is also a funny thing with high-dimensional statistics. Let's see. Yeah. Oh, sorry, I have to go back to. Yeah, cool. This Gaussian process here has a zero mean prior. Does anyone see a flat function? No. The highest density function, in this case, is the line. What's the probability of drawing that? Nothing, right? Pretty much nothing, because effectively the typical set, so the typical set is the set of a distribution. The typical set is the part of a distribution where typical samples come from. And when you increase the dimensionality, the mean is not in the typical set. It's basically one of the least likely samples you can draw from a Gaussian is its mean, right? And this is something that, if anyone works with diffusion models or flow matching, that's why you can't use them as density models. That was a side note. Cool. Shoot.
The first comment I would like to say is we are kind of taking under the roof the parametric part of the model, right?
Yeah, we have.
Because the covariance function has in itself some parameters. So the first comment is going in that direction. How do we handle that? It is still a parametric approach. And the other comment is there a specific reason why we are focusing in these Gaussian processes instead of, let's say, a Dirichlet process or any other kind of process?
Super good question. So the comment that I usually get when I introduce these things, if I've managed to do a good talk and people are kind of excited, then they say, oh, what other processes are there, right? And now you can think about Kolmogorov's extension theorem, and you can think about what distributions do we have that actually fulfills this. The beta distribution does, and that leads to a Dirichlet process. The Dirichlet process is a process over countable infinity instead of uncountable infinity. So it gives you partitions of an object. It's a really, really useful thing and really good to teach. The reason why I teach Gaussian processes is, one, I think they're much more useful, and secondly, you can do them nicely visual. It's much harder to do the Dirichlet process in a visual manner because they're discrete, right? The Gaussian process is kind of attractive in that way. So what I hope you'll all do after the talk, you'll be like, oh, that's good. Now I'll go and look into the other stuff, right? So absolutely right. It is tricky to define these processes, and not many exists, right, that we know of. So it is a bit challenging. Super good. Really important comment. So there's an elephant in the room, right? And this pink elephant in the room is not just what you brought up, the parameters of this thing. It's a slightly different thing. It's namely that, right? So this object here is an inverse of all the data points that I've seen, right? So now that has cubic complexity. And everything you do, so say for example, the parameters that I haven't done anything with, I just fixed them. You can make them learnable, right? That's very easy. You will just put a prior over them and try and derive the posterior over this, or you can do maximum likelihood on them. You can do whatever you want, right? They're just parameters of the model. You would do that on the object where you marginalized out the Gaussian process. That would mean, if I would do an iterative method, I'd have to invert this every iteration. So now say you've got 100,000 data points, well, I don't have enough compute to do that, at least, right? So this here is really, really annoying, right? So this would pop up if you would do, say something, I would do maximum, like people call this type 2 maximum likelihood, blah, 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 because you're marginalizing out one thing. Maximum likelihood, you're maximizing something, right? So say that if I do that, each evaluation of this is cubic in the data. You're not going to do that. So then another thing, that's the first annoying thing, that comes from the integration of f. But say that I'm now doing unsupervised learning, and I want to have some form of prior over x. You actually need to, because there's a trivial solution. Say if you specify a GP that likes flat functions, right? If I just push x as far as humanly possible away, you can make the flattest function known to man, right? So I want to fix the scale of x. So normally when we do unsupervised learning, we at least put a Gaussian on this, right? You can skip it and do maximum likelihood and trick a little bit, but normally we also integrate this out. So say that I now put a Gaussian on this. This here, as I said, is a distribution that contains effectively all functions. Now, think about taking a Gaussian, transforming that with any function, and that should come out on the other side. Well, you can't parameterize that. You can't write the math down for what that equation, that distribution actually looks like. So the integral over x is generally intractable. And that as well means if I want to do composite deep learning, right? So I put one of these and then another one and another one, that means that it's just never going to happen, right? So we end up in tractabilities straight away. So what I'm going to try and do is show you how we can address both of these at the same time. And we're going to do this with the same thing I talked about yesterday, building a variational bound of this. So basically, I'm going to simplify things a little bit more now. So I have an integral. Let's assume this integral is intractable, right? That's the object that I want. The slide I showed yesterday was saying, this is my model. I've defined this model. I want the marginal distribution over y. This I can't do. What I'm going to do is that I'm going to write down that integral using, well, base rule if you want to. I've just flipped this and this object, and now you've got base rule. That's effectively looking at this term is this term. So the dependency, how x depends on y. Now, my idea from yesterday was saying, that means learning this and learning this is effectively equivalent, right? Because this stuff I can do. So what we're going to do is rather than reaching this by this integral, we're going to start looking for this. And the way we're going to do this is we're going to put a approximate distribution of a family that we know. And then we're going to try and approximate this distribution with that. This is going to have some parameters theta. And the aim is that theta is going to contain all the statistics y transmit to x so that I can cut that dependency. Right? That's the ideal setting. Okay. So how do we then do this? Well, we're going to start with p of y. We're going to do the logarithm of p of y just to make everything easier. We're then going to write p of y, and I want some posterior terms in here. So I'm just going to write this. It's nothing, right? Cool. And then now I got the two terms I want to deal with. Now I also want the third term is my q term, so I'm just going to add a q here, and I'm going to assume that I'm integrating that out. This is just a constant, right? Log p of y, I'm integrating over x. This just integrates to 1, so I've done nothing. I've done nothing here as well, same story. And then I'm going to merge these terms. So I'm going to have this type of structure. Cool. And then I'm going to rewrite the posterior times the evidence as just the joint distribution. So I've got Q, joint distribution and posterior. And then I'm going to split this up. Now I'm going to split this up into a term that just contains Q's. I have Q log the joint, and then I got Q 1 over P of x to y. So the last term is the annoying one. Now I'm going to move that Q over to the last bit. So if I move that over, you have the equation that I just threw out yesterday. I got this term here, which only involves Q. I got Q and the joint. The joint should be no problem. And I got this red term here, which contains the intractable term. Okay? Now, what we're going to do, my image has removed. So the last term there is the KL divergence. And I just wanted to, how am I on time, by the way? We started a little bit late, so I'm going to squeeze some minutes there. 10 or 15 more minutes. Okay, so, right, then I'm actually going to skip this. So the slides that are coming here is just proving that this is a lower band. And we're going to exploit Jensen's inequality to do this. And the only thing I'm showing, I'm just going to show this very briefly. This last term, if I apply Jensen's inequality to this, so Jensen's inequality means that I can, if I move this log, because the log is the concave function, if I move this out, then I get a lower bound on this integral. If I do that, if I move this out, this q of x is going to cancel with this one, so I just get this, integrating a density over whatever I'm measuring over, it's just going to be 1, so it's 0, right? So I'm just showing that this thing is bounded from below by 0, and then I do another one where I just show if you say that q of x is the true distribution that we're looking for, that's the case, it's 0, right? Hopefully we've all seen this. So that object there is called the Kullback-Leibler divergence. It's a measure of divergence. It's not a metric because it's not symmetric. It's 0 and only 0 if q of x is equal to p of x, and it's always positive. And because that's true, we can go back to the previous formulation that we had, and, oh, no, sorry, that's just showing the other one. Sorry, we can go back to the other equation that we had, and we can now say, I got these two terms which I hopefully can compute. This term here is always positive. Now, that means that these two terms is a lower bound on that. And this is called the elbow, the evidence lower bound. And this bound is tight if q of x is equal to that. So that means, rather than thinking about this object, I can think about this object. So I'm going to try and maximize this object with whatever means I have. Now I'm effectively pushing q of x towards p of x comma y. So another sketch of this is just this, right? So I have log p of y, which I want to maximize, or which I have, and then I want to find a q that approximates this posterior. I'm going to maximize this term and thereby minimizing this term. So, went very quickly there. Great. I'm going to skip through these now. Great. So, fantastic. So let's just do this with Gaussian processes. Should be easy, right? So, now we're going to take the object that we had before. So, Q, joint distribution. Remember, I had f and x that I wanted to integrate out. We're going to focus on x in this case, because that's the really tricky one, right? F was just computational. X is the really nasty one. So, what I can do is I can split this up, right? I got my likelihood, I got my Gaussian process prior, and I got the prior on this. And And then I can try and nerdle out some form of bound from this. So I get Q of x and P of x, I've moved over to this side, and I get this term left here. So an expectation over the log of P of y given f, P of f given x. So I got a lower bound, and I got a KL divergence that says how close Q is to P, right? So how close the posterior is to the prior, right? Problem is I haven't simplified this at all, actually. I haven't alleviated any of the problems that we had here, right? I still need to push this thing through, right? So a basic variational inference mechanism does not work on Gaussian processes. You can't apply this. It's not going to help you at all. So we are going to do an approximation which is based on the notion that this is a stochastic process. So what we're going to do, we're going to take a non-parametric view to our approximation. So what I'm going to do is that I'm going to say I have a set of values that I've seen, f, with inputs x, and then I'm going to say I'm going to look at a slightly larger process. So I'm also going to say there's some points u, which I don't know what they are, and some points z, which I don't know what they are, but they correspond to each other and they're part of the same Gaussian. Now, let's think about what we knew about conditional distributions. Now, I can just write this down as this. I can say what I know about the current data, given the other data points that I've seen, that I haven't seen but I could see, its input and the input z to y, times the Gaussian process prior only over that object. So the marginal plus the conditional, right? Times the conditional, okay? Now, if I write that out, this here is just a conditional, like a predictive form of a Gaussian. This is exactly the predictive distribution that we got. Now we're doing the prediction in a really weird way, right? I am predicting the data points that I've seen from stuff I haven't seen. What we did before was the other way around, right? We said, I have seen this, what do these guys do, right? Now you can possibly see where I'm going with this, right? Now we're going to consider these things parameters instead. So what I'm going to do is I'm going to say, I have this stuff that I've seen, right? I do this the right way now. No, I have this stuff I haven't seen, which is going to predict the stuff I want that I have, right, that I've seen. Now I'm going to make those things learnable parameters. So I'm going to say, figure out your position as good as you can so you can represent me, right? And we call this inducing points. So what we do, we've done nothing at all to our model. We just said, I'm just going to look at a couple of other marginals, right? So now we've got this model. Instead, where u and f live in the same space, and y is the observations of f, so you can have a likelihood function between them. Cool. So now, remember what these distributions were. Now we're going to put variational distributions over these. Remember that variational distributions are approximations of posteriors. So q of u is approximating posterior of u, q of f is approximating posterior of f, q of x, right? That's what these actually should do if they learn. Now, what we're going to do is we are going to say, I want to find u's such that u's represents f perfectly without needing to know y, right? So I'm going to try and find u's such that u's are sufficient statistics of f's so I can cut the dependency of y. So exactly the same approach as before, but just this slightly weird thing about having, you know, these outputs of the GP as the variational parameters. So if I do this, there's a lot of equations here. Hopefully you'll get the intuition. So I'm going to take this object there, and I'm going to chuck in all the variational distributions, and then I'm going to split this up into the terms I had, right? Now I got this object here, right? That's just splitting this up into the likelihood, GP prior, or the conditional GP prior, and the GP prior, okay? And then, let's work with that. So, now I'm going to say Q, oh, did that not come there? Yeah. Now I'm going to say, remember Q of F that we had, I'm going to have a distribution, an approximate distribution of this, such that U is sufficient statistics of this. If I put that in, it will be this. So I'm going to make the assumptions, yes, U do represent all of Y, right? I think I missed something here slightly. Remember, this is Q of F, but I'm going to say U fully represents everything that contains in Y, so I'm going to drop that. Yeah? So when I put that in here, Q of F, I've dropped Y, right? And now you see something very nice. Dunk, dunk. Those two are going to cancel. So now, if they cancel, what I've done now, very happy to go over this on pen and paper with people. I know it's super quick. We can do this later on. Now, I've cancelled these two. I end up with this. What's the beautiful thing that happened now? This integral there, this part here, does not flow through this part. I've effectively I've cut the whole thing in middle. So now I have tractable integrals. So I end up with this here. I have to integrate. Remember, I picked Q of F to be P of F, right? So now I have to take the expectation over the likelihood function, this is probably very easy, with this GP prior. Cool? Most likely, this is Gaussian, most likely I have a Gaussian likelihood. Gaussian integrals, this we can do. And then I got a KL term, Q of U to P of U given Z. Right, this we can do, right? This is not rocket science, that's just the GP prior, and this here, I can pick to be whatever I want, right? Pick it to be Gaussian in your, you can actually do this in closed form. Cool, so now we've effectively done this. And there is a term that I dropped because the math didn't fit on a slide. There's another KL term, Q of X, when you do the integral over X, that just has been dropped, but it pops up again. So this here is the final bound on this thing. Cool thing is, with this, it allows us to put really cool priors over X. It allows us to avoid this integral, this computational thing that we had where the computation was cubic. Now it's cubic in U and linear in N, which is really cool. Because the only matrix I need to invert, is the prediction of U saying what F should be, right? Before we were looking at what F says the world should be like, right? Now I'm just looking at what U, and I choose U. So you can choose U's to be 10, right? Now you invert a 10 by 10 matrix. So you can do latent space priors, simple Gaussians. You can also do things like this, which is really useful. You can do something called automatic relevance determination. So if you do a latent variable model, you don't know how many latent variables you should have. Now you put a parameter, which you have a prior on, that says switch the dimension off if I don't need it, called automatic relevance determination. It's just a covariance that looks like this with an additional learnable parameter. You can do dynamic priors, where you can say on the latent space, each x should be close to the next x. Now you can do really cool things where you can simulate motion. You can do things like this, where you can stack Gaussian processes, because we've cut each of these layers in our bound. That has problems, but you can do things like this if you want to. And that is quite funky. So, I'm going to try and wrap up now. Basically, all models, all Bayesian models are generally computationally expensive and intractable, right? If you work with these things, I think in my lab, we would spend possibly not even 10% of our time thinking about models and 90% of the time thinking about approximations of them. Now, I think, though, as scientists, worry about the inference later. If we start fudging the models that we do, but because of what we can do, we are in a very tricky scenario, right? Spend all your time doing the right mathematical thing, and then let's meet up like this, and let's figure out how we can actually do inference in them, right? I really don't like when we fudge these things, right? I think if you got to my first talk, hopefully you got an idea of how I think about Bayesian principles, and then go off and see, if you look at the GP things that we talked about today, what you'll actually see, these are linear models. You'll see, if you compare the equations yesterday and today, they're actually exactly the same. They're just linear predictors. That's why they're so cool. So, just in summary, all things I've said, no free lunch. Now, I can only think about an interpretation of some data in terms of the priors that I put in. I think GP priors are truly, really remarkably interpretable. I think anyone that argues religiously about being Bayesian or not, it boils down to, do you believe in the process of marginalization? Do you believe about the notion that I just said, that I can reparameterize a space by stretching and compressing things? I think you can believe potentially pragmatically to be non-Bayesian, but it's very, very hard to say this philosophically. I think that's tricky. So non-parametrics is just thinking about models where you parameterize not the data, but you parameterize the relationship between data. The cool thing with this, which we haven't even touched on, they have infinite capacity. The more stuff you see, the more you can learn, right? It's a very, very useful thing to have. Models of non-parametrics leads to stochastic processes. There's a whole other way of explaining this through differential equations and so forth, but I like this explanation. Gaussian processes, practically, they're just simple manipulation of multivariate normals. They're utterly trivial. Theoretically, they're really cool and nice objects that contains lots of goody stuff that we can think about. So, are they then good parameterizations? I think they are. Being non-parametric allows us, it's only our lack of knowledge of appropriate measures of correlation that forces us to compromise. I think that's a question that I really like to address when I talk to people that have generated the data. I would say yes, because their parameterization is very well aligned with how we have knowledge about problems. Relative things make sense to me. And your point there, they're incredibly narrow, but super flexible. They can represent everything, but you can specify strong beliefs in a space of everything. And that's a rare characteristic to have. If you specify a polynomial of degree 14,000, you're going to struggle to say, but it's only these functions I really want, right? So, no more pink elephants in the room. I'm not going to talk about that, but therefore, end of 5. Thank you. Good. Do we have...
I have a quick question for you.
I had a slide for you, actually.
Oh, really? Oh, yeah. Awesome. Yeah.
But I didn't have time to go through it. Yeah.
Tomorrow. Maybe tomorrow.
We'll
Yeah.
talk about that.
But when you were talking about the Gaussian processes, and you were mentioning that the covariance structure is what you're mapping, and I think you're using reproducible kernel Hilbert space.
Absolutely. They're linear models in that space.
Exactly. But I was thinking, I've worked on support vector regression that they use the same elements, but they use them on the mean, like conditional mean. You're using it to model the covariance. Have you seen any similar approach, like doing that on the support vector regression?
So effectively, I think it is because you're looking at the prediction. You're learning the predictive model, and the predictive model, the covariance pops up in the mean, right? So too many slides to go back. But the covariance, no, we had it not too far. Where was it? No, why is this sensible thing to do? There was lots of K. Yeah, there.
Yeah.
The covariance pops up in the mean. So if you're only doing a model of the mean, that's exactly what a support vector machine regression is doing.
But could you end up avoiding like inverses, like the matrix inversion and other like tricky things?
So actually, this is super cool. So if you think about what a support vector is, that's you, right? It's exactly that, right? So it's actually, it would be exactly the same parameterization, and you only have to invert the support vectors in a support vector regressor, right? The rest is just a linear model, right?
Okay.
Yeah. So there's a really, I think there was this historically, right? So you had the whole community of kernel machine people, right? And then there was a slight, this is just historically, and then I thought, you know, there was amazing work happening there, and there was lots of really nice things. And then I think the Bayesian setting of this came in, started looking at this, and we kind of forgot about these things. Now, I think there's a lot of interactions needed to pick up on a lot of that work, because I think there is super clear connections, right? They are effectively the same thing. This is linear regression in a kernel-induced space with infinite basis functions. That is a support vector regression if you make it sparse, and that's exactly what I've done, right? So super good point.
Bueno, agradezcámosle nuevamente a Carl. Tenemos la sesión de fotos ahorita y el almuerzo. Entonces nos acabó el tiempo, así que la próxima podemos continuar con las preguntas y demás. Carl, thank you very much.
Perfect.